question. Today I would like to... all right, we can do that. Okay, a few things. A little bit about the rupture and the shaking effects. Well, about the context, really. I think for this question of complexity, I think understanding the tectonic context, I think, is becoming more and more important. And I know that Tom's going to follow up on some of that later on. So yeah, important to think about the context, the rupture and the shaking characteristics and effects. But also there's a big question still on the interpretation of the source. So it's already been mentioned that we need to merge the different disciplines together. And that's something I'd like to emphasize here as well, is that for me, the geology has not yet been incorporated into the understanding of the earthquake. So the faulting, yes, but not the geological context. So I'd like to emphasize that. And then that plays to this question of the upper plate structure or the subduction interface, or the subduction interface, and thinking a little bit about dynamic effects of large earthquakes as well. So if we get through all of that, I'll be very happy. Okay, the context, I'm sure most people know the New Zealand situation very well, or to some extent. Basically opposite dipping subduction zones connected by essentially a transform. But so in the north here around the Kaikoura area, we go from subduction, oblique subduction with strike slip zone, partitioned strike slip, into essentially a upper plate boundary. Okay, so we've got the subduction here, and in the North Island, the Wairarapa and the Wellington fault, and a little bit further to the south, the Marlborough fault system. Here's the seismicity. This is less than 40 kilometres, and a 10-year snapshot, I think above magnitude 3. So very much upper plate stuff. Well, that's probably, yeah, it's upper plate, but it's in the subduction zone. The back arc volcanism area, down through Marlborough and into the South Island. The Alpine fault is quite quiet, so similar to the San Andreas, quite quiet. The biggest fault in New Zealand is quite quiet, back and down into the subduction zone. The deeper earthquakes, very much related to subduction, and are getting deeper and deeper as we go to the west. And this quite steep subduction zone developing in the south, and no shallow earthquakes, of course, in the Alpine fault region. We don't need that. So just set the scene a little bit more. As we come into the northeast of the South Island, we have to the bit further west and south is the Alpine fault, but then that's the splay into the Marlborough fault system. Now it's interesting that if we look at in a cross-section through here across the main strike slip fault belt, and noting the relative plate motion here of 42 plus or minus 1 or so, 42 millimetres per year, if we go across this cross-section here, here's the best estimates of the slip rates. Long-term, probably 15,000 year average slip rates. Best estimate 4, 6, these are millimetres per year, 4.4, and on the Hope fault, 23. We get a best estimate of around about, let's say close, well, it's a bit short of the 42, but not far short. The minimum's about 10 millimetres below, and the maximum slip rate inside the bounds are actually exceeding the plate motion across the Marlborough fault system. So at least the majority of the plate motion is accommodated in the upper plate faults. And this here is just to remind us, this is on the Jordan thrust, which is actually this one here, that in the earthquake, Kaikoura earthquake, when we now see our new tools in our toolboxes, and we can see there are so many more traces than what we had originally mapped as the Jordan thrust. So almost certainly these are minimum estimates. because we haven't had the ability to map the small off-fault or smaller scale structures that are related to these fault zones. So it's my suggestion that even our best estimate slip rate here is a minimum because of where we know that the faults are a bit more complex, and we're not able, until recently I would say, to map all the strands of faults. Okay, so this number here with respect to plate motion is important in terms of asking the question about the role of the subduction zone in this transition from Hikurangi subduction to alpine fault transform. We're in that transition zone. The other thing that's important about this one here, and I'll show you the geometry shortly, this is the trace of the Jordan thrust, whereas the Kaikoura Mountains on this side are coming up and over the lower country. Actually, in this earthquake, the Jordan thrust moved with strike slip motion. So here's a fairly important fault. It's got 10 plus millimeters per year, and in different earthquakes it's had different kinematics. So when we're starting to think about, well, it doesn't fit and it's ancient faulting because it's got a different slip mechanism, here's an example from 2.5 years ago where a fairly major fault can have different movement depending on the complexity of the faulting. So that's sort of a bit, it's a bit unfortunate in some of our thinking. Anyway, here's some of the complexity of the faulting in this transition zone. We're in this Cook Strait region here as well. Mostly the Marlborough faults are taking or transferring motion out into the subduction zone. We're going from a transform system here so that these faults are transferring strain to the upper plate and then to the interface, and it's very much a partition system in the North Island of the strike slip faults behind subduction. There's the GPS strain rate. We see very high strains through the Marlborough fault system. This is the model for the Hikurangi subduction with the Taupo volcanic region sitting in behind. And from that, we have our current understanding of the National Seismic Hazard Model, going through the same zone, high strain rates, high fault slip rates. In terms of expected, was the Kaikoura earthquake expected? It is right in the highest zone of activity in the country. So in the region, we had somewhere between 0.5, 0.8 G PGA for 475 years. So it's the highest. To the north of the area, or the main faulting that took place in the Kaikoura earthquake, it's certainly within the highest strain zone, the highest hazard zone in the country. But here's the next one, a little bit about complexity. This is a model from the ground motions. Here's the PGVs, a model simulation of the earthquake sequence, starting in low slip rate faults in North Canterbury. Kaikoura is just there. So we're starting to see the radiated pattern. Not very much energy until about now. We're in here at 45 seconds already. Ruptures tending to go towards the north, and then we end up with a very, very large energy release on the northeast Marlborough fault system, Hikurangi fault, the Jordan thrust into the Needles fault, and the rupture propagation finishes here and this very nice poster outside showing the stopping point. So stopping is a really interesting question as well. Why? Why, how, when, and is that self-similar? Then we see motion. Here's some of the weak soils and basins and stuff effects as it transcends north, going up through Wellington. So in Wellington, I experienced the earthquake as at least 60 seconds of shaking. It was pretty substantial, and we were thinking, it's either alpine fault. It wasn't the subduction zone because it wasn't strong enough in Wellington, but it's clearly a big earthquake. So that rupture complexity we're seeing, I might just actually play that one more time because there's a piece in there. Come on, do it again. There's a piece in here I'd like to show. What am I doing? Okay. A very interesting part of this complexity as well, we are running? No. Stopped. Ah, here we go. So a little bit of high energy to the south of Kaikoura. As you'll know, it jumped over the Hope Fault, which comes right out at Kaikoura itself, so it was very lucky. The town of Kaikoura was in a bit of a shallow, bit of a lower ground motion area. But here, there's almost a suggestion of a rupturing back to the south again with some of this energy release from, and so there's a thought that there could have been even deep rupture of the Kekarangi Fault first, followed by more shallow rupture in two spikes of energy. So really pretty complex. You can see that there were these two clusters of strong ground motion. There's the horizontal motions and the vertical motions. The 3G here has been discounted now because of some very local effects at the strong ground motion site. But clusters here greater than 1G horizontal, and up here in the northeast, again at more than 1G horizontal and vertical. So very high nodes of activity, and you see that really in those PGV plots as well. In Wellington, so here they're not very high in terms of PGAs, but if we plot the spectra, then this is for, say, what's a mu value of 2, so this is a ductility factor in typical multi-storey buildings. This is a typical ductility factor in our code level, at this curve here. And you can see at 1 to 2 seconds, that earthquake, even though it's quite some distance from the epicenter, exceeded the code values by quite some distance. So that exceeded that 475-year ground motion expectation for the code by quite a bit. So for the taller buildings on weak soils, this is where these sort of buildings have suffered quite badly, and in fact there's been quite a lot of demolition of multi-storey buildings because of internal, just not practical to refit. So there's been quite a lot of damage in Wellington. If we go to the faulting itself, most people in this audience will have seen these plots before. There's the initial ruptures on faults down here. Some of these we had not even mapped as active faults. They'd had essentially no evidence of Holocene movement, but that's the initiation. Here's the Hope Fault, and it decided it wasn't going to participate. There's a little bit of triggered slip on it in some places. Triggered slip up to about 1 metre. That seems to be very isolated on pieces. Then it got into the Jordan thrust here, which this time acted as a strike slip fault, but it had this 90-degree intersection with this Papatia fault, which had the very big uplift, the very big coastal uplift. Then onto the Kekarangi Fault and the Needles Fault, and stopped about here. Interestingly, in 2013, we had these earthquakes, moderate magnitude earthquakes in Cook Strait, and there was still quite a lot of aftershock activity in this area at the time of the Kaikoura earthquake. So was that the reason there's a stopping zone there? A question. So you've seen very large displacements on the Papatia Fault. It's quite short, only about 30 kilometres long, but it's got 10 metres of vertical displacement on it, and then goes up against it, quite sharp angle with the through-going strike slip fault. This is where the high PGV energy radiation was from. This is where there was 12 metres of strike slip movement on the Kekarangi Fault, and it continued offshore. There's many people in the room that have contributed to this team and the wider team that came to map active traces. So the surface ruptures are very complicated. Some of it's very expected. So it's that funny combination of if it had started here and then sort of bled off onto some secondary faults or something, maybe that's more expected in some sense. But this went the other way around. Started with very rare events on these faults in North Canterbury, and then jumped on to something that was much more expectable. So you will have seen various pictures here. Wooden frame houses that can sustain 12 metres or 10 or 12 metres of strike-slip movement and still remain somewhat standing. Very nice fault scarps here. And of course, in terms of infrastructure, this is the Kaikoura landslides along the coastline, etc., etc. Some of the coastal uplift story. Here are subtidal seaweeds. These grow below low tide, so between the two strands of the Papatea Fault, more than 6 metres of uplift. Stranded happen very fast because some of the fish, the small fish that live in that seaweed and are pretty mobile, they even got stranded by the uplift. So the uplift is essentially instantaneous if even fish cannot escape. So there was lots of, in New Zealand we say kaimoana, the seafood. For a day or two, there was plenty of seafood there. But after a short while, it was also very smelly. Here's some LiDAR from before and after 2012 LiDAR from piece along the coast. And this is the Papatea Fault as it ruptured across the beach ridges. So anybody that tells you that you cannot rupture sand on a beach, it can happen. And did happen, and so between the two strands here was the very high area, quite localised uplift. On this little point here though, there are two higher Holocene shorelines. So we're wanting to now still find out what's the age of those earlier uplift events as well. There's a lot more work going on all of these faults to get a longer history, see if we can see what participated in prior events, but that information isn't really available yet. So here's a long profile, coastal profile. It's sort of copied and pasted from it's not very clear unfortunately. This covers, there's about 90 kilometres or so of coastline from the south, where there's a little bit of subsidence. This is where we come to the Hundalee Fault, the southernmost fault as it went offshore. Further offshore probably it's this fault that was part of the source for the tsunami, modest-sized tsunami fortunately. Around Kaikoura Peninsula, about 1 metre of uplift. In here between the two strands of the Papatea Fault with up to 6 metres of uplift. A little bit of subsidence or not much to the north. And then north of the Kekarangu Fault, there's a reasonable amount of uplift for a while until we get up to the northeast where the rupture finished and the uplift also had finished. So lots of new data in here. Some of it is published by Kate Clark and lots of colleagues from lots of different field observations, but a lot of satellite techniques also. So it was a really nice record. Here's some of the impacting stuff. It took a year for the road and the rail to open again. This is the main railway along the east coast of the South Island, the main #1 highway in New Zealand. So real big, I won't go into that much today, but real big disruption to the farming, the tourism for quite a long time. So I want to just make the point here that what we're seeing, here's the published fault source models. Now, of course, these come out quite quickly. Here's 2000, and there might even be a 2016, no, it was 17. So the first of them came out in 2017 based on INSAR, GPS, etc., etc. Here's the number of faults that can satisfy the teleseismic picture. So yes, there was some obliquity in the USGS source, and immediately people picked up, oh, there must be subduction involved. So all of these, here's in this column here, of these solutions, here's the number, the percentage of the moment that was supposed to be released on the interface in this earthquake. It was based, it's teleseismic data, or it's INSAR, or it's GPS, or whatever. Very little of the geology was involved. We come to the last couple of down here, the SESCA model. It was 2017. It it recognised 3 faults, but I'll come back to it. It did have some really thoughtful, was quite a lot more thoughtful in terms of how to assign the obliquity or the thrust component in the teleseismic. Ian Hamling's work later on, 2017, but had included some of the field observations of active faulting and also the coastal uplift in its solution. And by then they were getting to, needed to have, or in the model at least, 11, 12, 13 faults in the model to fit the solution, fit the composite focal mechanism. Here's some of this is actually from Ian Hamling's. So derived the model in the end, the model is derived from INSAR GPS, some surface faulting and the coastal uplift, and of course the seismological data. But given all this, there's still some significant residuals to the model. So there's lots of them. There's 10 very different models, all fit the composite focal mechanism. So what does that mean? So I think that's a sort of a cautionary note that this would be improved by that integration of the geologic record, and what I'm going to show today is that largely up until now that geological record has still not been considered within the likely source mechanisms. This is to think about, was subduction involved? Certainly the focal mechanism's got a thrust component, but there was a very quick interpretation, thrust equals subduction. So that's why I was saying in the first place that the upper plate fault slip rates essentially accommodate all of the plate motion. And as Harold Wellman, one of my teachers from a long time ago, he was rather facetiously saying that in those days, this fault is surplus to requirements. Playing the game as, we hold on to plate tectonics as being the gospel. It's another question to ask. There's some pretty significant, these are net maximum displacement. So I've highlighted the ones where we're above about 2 metres of all of these different faults. So there's quite a few that at the surface had more than 2 metres of displacement. We can think about that in terms of the net. So we've got a lot of net displacements here in the multiple displacement range. This is all coming from the surface faulting. And here I was wanting to suggest when we, with Nicola Litchfield and a group of us, we thought, well, it's time to bring the active fault data to the fore and think about what that means in terms of seismic moment release as well, to add to the conversation about bringing all the disciplines together and was subduction involved. When we do that, we can just look at looking at displacement and thinking about the dimensions and turning that into a seismic moment, or we could also look at some of what we've used in New Zealand as a magnitude length scaling relation as well. So we've got a couple of methods here of how to derive moment and magnitude from surface faulting. We can see that here the needles, the big contributors here are the Kekarangu. Well, this is going from the Needles fault all the way down to the upper Kowhai. So that's the Kekarangu fault and others. That alone is about 7.5 magnitude of the supposed 7.8 or so. From the geology, we would see a best estimate of 7.7 within a range of 7.5 to 8 based on surface faulting alone. So we don't really see, from a geologic point of view, much of a need for very much on a subduction zone. But we do need to explain where the thrust component came from. So this is really talking about this. Some of the best fitting models have that inclusion of the interface in some of the early solutions. Here's the USGS CMT. Some of the first solutions were saying 60% on the subduction zone, which has huge implications for hazard in New Zealand. when it has never been in the model. It's never thought that there's an active subduction zone below Marlborough, and so this has huge implications for hazard, if indeed it is active. The early solutions jumped to that very quickly. This is the Hamling model, and this is the component that might have been in that solution on the subduction zone. You can see here through the colour scale here, as much as 20 metres or so of slip on the bottom of the Kekarangi fault. Comparatively, the residual, if you like, on the interface or something was 4 or 5 metres. So that's more like what was the uncertainty from our surface geological measurements. All of them, everything seems to satisfy the CMT, no matter what model you got. So these solutions are by no means unique. They're made with a lot of data, but they're by no means unique. What I like about some of the early stuff, there was some of the solutions that were made began to question really whether it's the interface or some shallow dipping fault that was responsible for the uplift and also some of the convergence that is in the CMT solution. So this is from Vaso's work, published 2018, I think. So I wanted to explore just for a moment, still continuing this theme of was subduction involved, to look at, go back to the geology. Okay, I'll just go through this really quite quickly. The rocks of the region are these Mesozoic greywackies. Yeah? The geological history of these was, these are originally, they're weakly metamorphosed. They were in a subduction setting, Triassic, early Jurassic, essentially an accretionary wedge of an early mid-Cretaceous subduction zone. There's a period of extensional tectonics through here. This is the opening of the Tasman Sea period, lots of extension. There was some convergence in early Neogene as the plate boundary, the present day plate boundary developed. And then from the late Miocene to the present, there's a strike slip faulting as dominated. So we've had over the region, the geologic history of the region, it's pretty complex. It's subduction oriented. One expects in subductions all sorts of interesting structure to be there within the current geology. So I think there's multiple faults with varying dips and strikes are likely connected at depth through the Kaikoura region. So it goes back to, so that hasn't really played into yet the thinking about the progression of faulting, why some faults were involved, why some were not involved, and what actually makes the physical linkage perhaps that allowed these disparate faults all to cascade into what we're calling a single earthquake. Another interesting point here is that when you look at the metamorphic grades across this region, over a distance of about 60, 70 kilometres, you stay in the same metamorphic grade. So it's actually pretty hard to do. Because when you think about, I'll show you the next one. Here's a more similar idea. So this is through the Southern Alps, Alpine Fault. So at the Alpine Fault turns the whole of the crust up on the end, so you see at the fault you do see high-grade rocks. But when you think about the low-grade metamorphic rocks, they're probably at most 10 kilometres thick in a depth section through a crust based on pressure and temperature considerations. But when we look at Marlborough, we go 70 kilometres and stay in the same metamorphic grade. So really the only way you can do that is say that we've got between these currently active strike slip faults, the Greywacke basements, it's generally steeply dipping, but it's broken into these intense broken formations and melange that represents reverse faults or thrust faults from an earlier history, which are spaced 5 and 10 kilometres apart. So it's imbricated in these listric faults spaced at maybe 2 to 5 kilometres, presumably into a detachment surface of an earlier subduction zone, and this is how you can get the same metamorphic grade over such a broad area. that has not been considered in these interpretations of structure up until this point. So, I'm going to go down. Come on. Go. Do this for me. It's decided it wants to do something differently. Okay. So as I say, we can see that if we look, we can think about that with respect to what's happened in the Southern Alps, and we can think about what would be a normal thickness of these low-grade metamorphic rocks. The other thing we can look at too is think about in the Wellington region, some deep seismic profiling across the southern North Island revealed the Wairarapa fault, the Wellington fault, the Wairarapa fault and others as becoming, we think of them as vertical strike-slip faults in the surface and behaving purely as strike-slip faults. It looks as though the geometry is that they are listric down onto the interface. So this is just a little bit further along the margin. So that's, to our thinking now, a likely scenario for a deep crustal cross-section across the Kaikoura region as well. So that needs to play into our thinking. I remind you that here in the Wairarapa fault, this is where Rogers and Little documented the 18 metres of displacement in 1855. So 18 metres of strike-slip displacement in the 1855 earthquake. So we had 12 metres of displacement on the Kekarangi fault. I wouldn't bet that the Kekarangi fault does not become listric into mid-crustal depths. So we come back here to this idea from Seska et al. That rather than talk about the interface, maybe we should be thinking much more about these upper plate faults that become listric, and maybe that's where the reverse component that we see in the composite moment tensor is coming from. Having said that, here's the striations, the slick lines on the Kekarangi fault rupture in 2016. So there's no doubt it will strike slip at the surface. But yeah, how does it behave as it goes to depth? I think it's an interesting question. Right, of course we did have some residential damage built and the like, a bit of lateral spreading here for good measure and a bit of liquefaction. This is one of the very few collapsed houses. One of the two fatalities in this earthquake occurred here, 1880s unreinforced concrete building. So not too bad. The dynamic effects, we need to worry about we know that there was dynamic effects from this earthquake. There was tremor, slow slip events were triggered throughout the Hikurangi subduction margin from this earthquake, at 500 kilometres away. For the first time ever, we saw all of the slow slip patches in the Hikurangi margin light up within 1 week of the Kaikoura earthquake. There was changes to the geothermal systems, to water levels, etc., over wide areas. So the Kaikoura earthquake, as a largely upper plate event, did trigger a response in the subduction zone. And the subduction zone, of course, is what we worry about, because it's certainly got the capacity for magnitude 8.5 or more. So we were pretty nervous there for quite some time. Nothing has happened, but we were certainly giving the civil protection groups a warning that, hey, weird things are happening in the subduction zone we have never seen before. So for us, that's raising the question of the importance of considering cascading perils. But we also think about cascading perils in terms of time-varying hazard models. So how are we going to go forward in our community and think about these dynamic effects much more, because those are probably the things driving hazard as much as the time invariant sort of long-term average things. So we're certainly seeing some of that and actually had to face up to that in a nervous time over the last couple of years. This was the advice we provided in 2017. Scenario 1, and we came up with some numbers here, the 54% likelihood in the next year that the aftershocks would continue to decrease, but a magnitude 6 plus remains likely. Actually, we're probably still in that window. That's what's playing out to the moment. Scenario 2, thought to be unlikely within the year, that maybe at this hold point here, we were going to have some triggered, a long strike triggering into those faults in the Cook Strait area, some of which are capable of reverse and strike slip motion, and as we saw earlier, possibilities of tsunami with very short travel times into places like Wellington. So that was also one of the advices, somewhere between in the 7 to 7.8 capable faults in Cook Strait. Scenario 3, very unlikely, but don't discount it, that this could trigger the locked part of the subduction zone. So that was considered to be unlikely, but we should be somewhat prepared. So, lessons. There's some rules about step over zones and stuff. In these complex domains, I think we should be starting to think about applying those rules very cautiously. We see here in Kaikoura, maybe all of these disparate faults may well be kinematically or physically linked at depth via these deep structures. So how do we think about that? In these strongly imbricated terrains with multiple phases of deformation, we should be thinking about these connectivities at depth, and that should be part of this integrated multidisciplinary thinking all the way along. Otherwise, we'll be applying rules, so-called rules, when they shouldn't be. I guess I'm thinking in these complex domain, anything that's, well, and actually we saw in the recent sort of large earthquakes are almost certainly likely to be complex, and they can lead to cascading events. We saw that recent earthquake in Taiwan at 6.4. They're talking now about 3 different faults that all ruptured in a magnitude 6.4. So here, 80% of the moment was released on the Jordan-Kekarangu Needles fault, the straight through thing. That was a very expectable event. Last event 300 years ago, average return time something 2 to 300 years. So 80% of the moment release was very expectable and already in our hazard model. Is that good? Is 80% good enough in complex terrains? I'm usually happy with an 80-20. We've got to try and strive for this complexity and multi-segment in our historic and geologic records. We have to go there, but I think we've got to be very careful to not to step back from what we do know and say we don't know anything, because that will lead us into a very bad place, into very dark places. And I think some of these smaller faults, maybe the other way around, some of these smaller faults maybe very frequently rupture with the big events, but we haven't focused upon those in our seismic hazard or paleoseismic studies to know whether that's the case or not. So that's an open question, I think. For us around this question of resilience, going beyond geology and paleoseismology and hazard into resilience and risk and stuff. From a land use planning exercise, we're a rural earthquake, not too much problem. Minimal liquefaction, not too bad. The landslide impacts on farming were pretty big, but what do you do in a farming country? Maybe there's going to be some changes to on-farm practices in terms of farming. Infrastructure, no surprises to scientists, but you know, that road and railway along that coast the rocks were waiting to fall down. In the port city in Wellington, in the port, there was evidence of a lot of neglected maintenance, and in fact some pieces of our critical infrastructure had not been maintained to the level of a critical infrastructure. So there's a few heads that should roll there. So we've got some evidence, some pretty weak risk management practices in some of the infrastructure communities. And then this business continuity planning, that's always a constant issue to keep people on the go. So some final things, very quick thoughts about further research. Yeah, this question, is there subduction under North East South Island, is hugely important for our national seismic hazard. I think we need to understand the social and economic impacts of events like this, because it's not so infrequent. It's probably something like a 100 to 200 year event for New Zealand. So are those impacts acceptable? Is the risk we're taking unknowingly perhaps acceptable? These longer paleoseismic histories are so much needed to see whether the evidence of multi-segment rupture is obviously important to chase. And I think the secondary faults that may or may not, do they only rupture with the bigger events that are in the nearby area is a question, I think. We're looking closely at the sediment cascades out of the ranges. There has enormous environmental in the land, but also in the marine environment. So there will be a multi-decadal impact from the erosion now from the mountains to the ocean, which will have big effects. And it leads to us understanding too, we got the alpine fault sitting there quietly with 30% chances in the next 50 years in the alpine terrain of the South Island. So this is giving us a heads up about what sorts of effects we might see then. And then this dynamically triggered stuff, I think, is really important for our community to think about in terms of seismic hazard as well. So how do we build that into future hazard models? So yeah, with that, press that button. Thank you.